Okay, we're going to continue on here with chapter 4. Bless you. And we were talking about in chapter 4, really a continuation of chapter 3 and bonding. We were talking about geometry. We talked about two types of geometry, electron pair geometry. And we talked about molecular geometry, which is also the shape of it. Really, the best way I think to do it, as we talked about, is really sort of memorization, number of electron pairs, number of bonds. That's usually, a good way to look at it. So remember that pretty much the number of electron pairs will dictate the electron pair geometry. That is, again, the arrangement of the electrons around the central atom. And as we saw when we have pretty much structures where there are no lone pairs on the central atom, so no dots when you draw your Lewis structure, both the electron pair geometry name and the molecular geometry name will be the same. And that is because pretty much all the electron pairs are bonding electrons. So as those bonding electrons move, so does the atoms that are attached. And obviously the shape of the molecule stays basically the same as the electron pairs. It's only really when we introduce really non-bonding electrons on the central atom that we get a difference in the molecular geometry or the shape. And that is because when we have the non-bonding electrons, instead of having a actual bond and atom tied to those electrons, it's kind of open in a sense. It's not really attached to an atom. So there is a greater repulsion here between our non-bonding electrons and our bonding electrons. So what ends up happening is we get these guys that start to go as far as they can. But once again, they do run into the kind of bonding electron on this end. So, they'll kind of spread out as far as they can to sort of maintain their happiness here. And we end up with some different shapes, like, say, trigonal pyramid here. That may happen in that case. So once we start introducing the non-bonding electron, what really happens is we get the repulsion forces that occur. The worst sort of situation is where you get non-bonding electrons near non-bonding electrons. They really don't want to be near each other. And because they're not really tied down by an atom through a bond, they can actually move a little bit more. And again, that sort of makes the overall shape adjust as well. That's why we also see a little bit different sort of bond angles when we have non-bonding electrons there. We get a little less than a normal sort of bond angle when we have all bonds, again, because it has that little bit more room for movement. We also saw perhaps some new geometries for a lot of you, which go with the expanded octets. So we have our sort of 5 electron pairs around the central atom, or 6 electron pairs around the central atom. Remember that when you're doing geometry, if you have a double bond or a triple bond, we do count it as only 1 electron pair and 1 bond. So that's a really major sort of thing to keep in mind as you do geometry, and really only geometry. 1 electron pair, 1 bond. They're effectively moving as a unit, and that's sort of how they are treated when we do geometry. Any questions on any of that stuff there that we talked about? So clearly you are responsible to know how to identify each of those names. And we're going to continue on then. And we're going to continue on then talking about another sort of bonding theory. And this is what is known as hybridization. And hybridization kind of deals a little bit with a different sort of idea of how sort of the bonds come together. It accounts for, in some cases, some of the angles and bond angles that we do see. That may be Lewis theory, which is sort of the Lewis structures, and Vesper maybe won't account for. So the idea of obviously a covalent bond, as we talked about, is overlap of our orbitals. Or these are both sort of s orbitals here in that sort of overlap region. That is ideally where the electrons would be shared between the 2 atoms, obviously being attracted to the nucleus on both sides here. And as we talked about, the sort of mutual attraction of those electrons to the nucleuses there sort of ties everybody into place. And we get our like covalent bond here that we have, say, in hydrogen H2. Now, the idea of sort of hybridization is a hybrid orbital is made from basically the combination of different atomic orbitals. So we're clear when we talk about atomic orbitals, those are S's or P's or D's and so forth. So those are atomic orbitals. Now, if you think about just the sort of theoretical shape of these different orbitals, they are different shapes. Like an S, right, is a circle, if you will. A P is sort of like a figure 8 shape and so forth. And they're also sort of on different energy sort of levels, if you will. And that's based on sort of our electron configuration, right? We have these orbitals that are not exactly equal with each other. So the idea of these sort of orbitals just kind of coming together, might not always work very well when we're kind of putting, kind of like a round circle with a teardrop sort of shape, and they're at different energy. So the idea of hybridized orbitals is we take a couple of these orbitals, or maybe more, and we kind of mix them together. So we mix some of these atomic orbitals together. The result is what is referred to as a hybrid orbital. The hybrid orbital typically will have the same shape. It will also end up being at a little bit lower of energy and the same energy as the other hybrid orbital. And all these things sort of benefit the idea of these orbitals sort of coming together a little bit better, a little bit more stronger in terms of their bonding, as a result in the same shape and same energy. So again, like putting two things that are identical together versus two things that obviously are a little bit different. Now, the deal is for every total number of atomic orbitals you mix, you get that number of hybrid orbitals. So for example, in my circle here, I mix together an S orbital and a P orbital. The result is I will gain basically two hybrid orbitals that are again the same shape. They're at the same energy and going to allow for some better sort of bonding to perhaps occur. If I mixed, an S and two P orbitals together, that would be three atomic orbitals. That again would result in three hybrid orbitals being made. So however many atomic orbitals you kind of throw together in the mix there, you will get out basically the same number of hybrid orbitals. Any questions on that there? Yeah. So let's take a look at some of these sort of hybrid orbitals and hybridization and sort of how we kind of go through it. Really, the simplest hybrid orbital that you could have is what is referred to as the Sp hybridized orbital. Now, hybridization follows the electron pair geometry. So hybridization follows the electron pair geometry. And to be truthfully honest with you, people go like, how do you figure out the hybridization? There's, a pretty simple sort of way you could do it. There is basically one S orbital, right? And P orbitals, there's 3 of them. And D orbitals, there are 5 of them. And basically what you're looking for when you draw a Lewis structure and you're trying to apply hybridization to a particular atom is you basically want to count up electron pairs. And it doesn't matter if there are bonding electron pairs, non-bonding electron pairs. You want to count up electron pairs the same way as you do with geometry, which means if you come across a double bond or a triple bond, once again, it counts as only one electron pair. And then you basically count it off. So in this particular case, we're going to take an S and a P orbital and hybridize it. And that's going to give us basically 2 Sp hybrid orbitals. So we will get 2 of these Sp hybrid orbitals out from this hybridization occurs. Here you can see the s orbital. There's our p orbital coming through there, our px orbital. And when they kind of come out, badly drawn here, but kind of like kidney shaped, if you will, they kind of make these hybrid orbitals that sort of have that sort of kidney type shape. And there's basically 1 and 2 hybrid orbitals, and it has a bond angle of 180 degrees. So if you think about our electron pair geometry, something with 2 electron pairs is linear in terms of electron pair geometry, and that goes basically with the sp hybridization. Don't overthink it. S and P is two electron pairs. Sp2, that is the hybridization basically for anything that has 2 electron pairs around it. So if we take a look at an example, what actually happens through sort of the hybridization process, if we look at BeF2 and Be is 4, this is the electrons in beryllium, electron configuration 1s2, 2s2. It's got 2 valence electrons, and that is the 2 valence electrons. Through the hybridization process, what happens is you will always get sort of a promotion of a lower electron to a higher energy level or higher orbital. So usually this electron here will promote itself upwards into that p orbital. The result is now we have an electron, an unpaired electron in a p orbital and in a s orbital. And this is what's going to go through hybridization here. We're going to take this p orbital, this s orbital, and these guys are going to go through and hybridize. In this case, we took an s orbital and a p orbital. That is 2 atomic orbitals. That will yield us 2 hybrid orbitals that are now basically the same shape, a kind of kidney shape, if you will. And they're also the same energy. So it brings everybody down to sort of equal with each other. And that's going to allow each of those guys basically to make a bond. And who are they going to bond with? They're going to bond with basically fluorine. So this guy has the ability to make a bond with a fluorine. This guy has the ability to make a bond with fluorine, and that would account for the bonding that would happen in this particular case. Now, what also happened through this hybridization is I am also left with 2 unhybridized p orbitals. So we have 2 unhybridized p orbitals, which would be py, by the way, and pz. And these are regular run-of-the-mill, still figured 8 type shape p orbitals that are unhybridized, and that happens. That's going to be really important later on when we talk about sort of multiple bonds. Those guys sort of come into play when we make basically double bonds and triple bonds, but we do get these sort of unhybridized p orbitals that occur. Any questions on that? The next type of hybridization that we'll talk about is one where we have Sp2 hybridization. And much like the name implies, we're going to take 1 s orbital and basically 2 p orbitals and hybridize it. And if you do, again, you can see that is our bad color choice, apparently. Try a different color. That is our, again, s orbital. There is our p orbital and our other p orbital coming out through that way. Again, since we hybridize 3 atomic orbitals, this is going to yield us 3 equivalent Sp2 hybrid orbitals. Once again, it has the sort of kidney shape. It has a bond angle of about 120 degrees. And it is this simple. That is basically 1, 2, and 3. So that corresponds to 3 electron pairs, basically. And the electron pair geometry of 3 electron pairs is our trigonal planar. So trigonal planar electron pair geometry goes with Sp2 hybridization when you have that as your electron pair geometry. So they are tied together. Once again, this will also leave us, as we will see, an unhybridized p orbital. So if you kind of do my little thing here with an s, maybe an S. There we go. S. There we go. P. energy. We took this, this, and this, so that is going to leave us again that one unhybridized p orbital that will be there. In this case, it will be the pz orbital that is available. So an example of this would be boron trifluoride, and once again, this is boron, which is 5, so that is 1s2, 2s2, 2p1. That is the 3 valence electrons in boron we are looking at here. We're going to get this same sort of promotion that's going to happen through this hybridization process. So this lower electron is going to go up, and much like electron configuration, it will then go into here, right? The next orbital over, which would be the py orbital. The result of that is we will then get 3 unpaired electrons, 1 in an s orbital and 2 in our p orbital. That is going to make these 3 guys basically go through hybridization. Once again, here we just basically hybridize 3 atomic orbitals, which will give us 3 hybrid orbitals that once again are the same shape, same energy, and that allows each of those hybrid orbitals from boron to basically make a bond with a fluorine. So each of these would then go off and basically make its bond with the fluorine. Once again, here we have an unhybridized pz orbital over here. So again, just our regular sort of p orbital that is unhybridized. So sp2, and literally you just count the letters. sp2 is 3 electron pairs, trigonal planar. That is how it should work, as simple as that. People like to complicate it. Why complicate it, right? Another hybridization, which is very common, is Sp3 hybridization. And Sp3 hybridization, much like the name implies, we're going to take basically our s orbital and all 3 of the p orbitals in that subshell, going to mix them together. The result there is we are going to get this shape here that we see that has a bond angle of 109.5. The geometry with a bond angle of 109.5 is. So we took here an S and 3 there. That's a grand total of how much? 1, 2, 3, and 4 electron pairs. 4 electron pairs then would be tetrahedral, right? So tetrahedral electron pair geometry is our Sp3 hybridization that occurs. And again, here we will end up in this case, which actually 4 Sp3 hybrid orbitals as we combine basically the S and the 3 p orbitals together. Again, giving us 4 hybrid orbitals, same energy, same shape, going to allow some better bonding. An example of that would be methane here. So this is the carbons, valence electrons, carbon 1s2, 2s2, 2p2. That is the 4 valence electrons. So once again, through the hybridization process, our lower electron going to come on up to our empty p orbital up there. The result of that is now we're going to basically take all these guys here and go through hybridization. That is going to get us now 4 equivalent Sp3 hybrid orbitals, all with basically an electron to share, basically. And in this case, they are all going to make a bond with hydrogen. So those are our 4 bonds between carbon and hydrogen in this case. By the way, hydrogen orbital will still be the 1s orbital, as hydrogen will not go through hybridization because frankly it only has 1 electron, so it will not go through hybridization. These will still be regular 1s orbitals. Yes. It does, because it's going to go fill basically an empty orbital, and as we talked about electron configuration, always the first one in has the plus half spin, right? So as it goes up there, it will be promoted and have sort of that upwards direction, because it technically will be then the first one in that particular orbital. Yeah. Yeah, usually it's just one electron that will kind of get promoted up there. And most things that you do, it would just be that one electron that'll get promoted up. So usually you won't see probably both get promoted, unless you get in maybe some that have some already promoted in transition metals, which we don't talk about and stuff like that. But in stuff that we deal with, usually it's just the one sort of electron lower that goes up. Now, as we will see shortly here, when that one electron goes up, it may not have anywhere to go but to pair off with somebody. So that does happen, but it is typically just the one electron. Other questions? All right, so we can just look at this and figure it out. The hybridization, just so we're clear. In this case, usually you want to kind of lay up your Lewis structure first, and really, if we had to do the hybridization from our Lewis structure, really the no-brainer way is just to make that sort of like electron configuration type deal, and basically just go central atom, 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds. I use an S and 3 Ps. So the hybridization here would be Sp3, and you should again always sort of get it correct in that case. Now, to sort of answer that question or that we were just talking about there. Now, in certain cases, when we get that promotion of that lower electron up into the p orbitals, there's already electrons pretty much there in all the orbitals. So that electron does need to go somewhere else. So a hybrid orbital can be occupied by basically lone pair electrons. So when we draw our Lewis structure around the central atom, we got dots sometimes. And those also can be sort of accommodated or accounted for with hybridization as sort of being already sort of paired off as that occurs. So that does occur with NH3 and H2O, and we'll look at those here in just a second and sort of explain, what happens and where the electrons sort of go. Now, when we talk about bonding with sort of orbitals, there's a couple of different types of bonding, but pretty much the first type of bond, maybe a bad description, but like the first line that you draw, like the single line, even the first line in like a double bond that you draw, or the triple bond that you draw, these are what are sometimes referred to as sigma bonds. And sigma bonds basically describe how the orbitals come at each other. And basically with sigma bonds, they pretty much go right at each other, kind of head to head, squished together. And that area that kind of squishes together is the area where we have the electrons basically being shared. So a simple way to sort of identify, is this a sigma bond or not, is pretty much like the first line that you draw that makes a bond in a Lewis structure, and the first sort of line, if you will, in a double bond or a triple bond. So hybrid atomic orbitals result, as I said, in a stronger bond than both unhybridized orbitals when they come together at different energy and different sort of shapes. So let's take a look at NH3. So NH3, if we drew it, and I think we drew it before, will look something like this. So this is NH3, and basically, if we wanted to figure out the hybridization here, once again, we want to count up electron pairs on our Lewis structure for the element that we're going to hybridize, which is the N. And it has 1 electron pair, 2 electron pairs, 3 electron pairs, and once again, 4 electron pairs. So we count electron pairs the exact same way as we do when we're doing geometry. Doesn't matter if they're dots, doesn't matter if they're lines. And again, if they are double bonded or triple bonded, they count still as 1 electron pair. So if I wanted the hybridization here, this would be, I got 1, 2, 3, and 4. The hybridization here for our nitrogen is Sp3 hybridization, because it basically has got 4 electron pairs around it. It goes with the tetrahedral geometry. So if we look at nitrogen, which is 7, 1s2, 2s2, 2p3, it has 5 valence electrons. So what happens with our nitrogen is we have our 2s electrons, we have our 2p electrons, where they each have basically an electron in it. So that is nitrogen, obviously, before the hybridization. What is going to happen in this case is we are going to go through the hybridization process. So as we talked about, that lower energy electron is going to go up. At this point, it should end up where? Yeah, because we basically did one in each, like electron configuration. So this one will now promote into basically that box right there, just like you would feel it as you're doing an orbital diagram for electron configuration. The result of that through that promotion is we'll end up with the 2s that has an electron. We'll end up with our 2p orbitals here that basically look like this. Now, because this is hybridized as Sp3, that means we're actually going to take everybody here, right? The s orbital, bless you, and all three of the p orbitals are going to go through hybridization. Because I hybridized 4 atomic orbitals, I should end up with how many hybrid orbitals? I should end up with 4 hybrid orbitals. So I hybridized 4 atomic orbitals, gives me 4 equivalent Sp3 hybrid orbital. Now, when we look at it, we got a guy that's paired off. We got 3 of them that now have basically single electrons. And once again, this is the hybridization on our nitrogen. At this point, we can now really account for all the bonds and everything that we see around nitrogen by telling what happens. We'll call this bond right here, call this guy bond number 1, just for the sake of argument. Bond number 1 would be between our nitrogen and a hydrogen, 1s orbital. That would be bond number 1. Bond number 2 would be, say, between this nitrogen and another 1s orbital of hydrogen. And bond number 3 here would be between this guy and, again, running out of room, not drawn correctly in terms of energy, but we'll just kind of squeeze it in there. We have now our 3 bonds to hydrogen. Now, what is left on the nitrogen? It is the lone pairs that we see right there. And that would be these guys right here that basically got paired off through the promotion process. So these would account for the lone pairs that we see on the nitrogen. So this hybridization sort of model here accounts for all the electrons and all the bonds that we see in NH3, even the ones that are not bonds, the lone pairs as well, that we can see happen there. Any questions on that there? This also occurs with, say, something like water. If we look at something like water and we want to kind of figure out what's going on with it, so let's take a look at that. So if we drew the Lewis structure for water here, what is the hybridization of the oxygen here? The hybridization of the oxygen is... So again, we would go to the oxygen and we would count up our electron pairs. That's 1 electron pair, yes, 2 electron pairs, 3 electron pairs, and 4 electron pairs. If I just count it off here, starting with S, 1, 2, 3, and 4. So the hybridization here for the oxygen is Sp3, yeah? So the hybridization here would be Sp3. I took an S and basically 3 p orbitals. So the hybridization here for this oxygen Sp3, remember, is basically the total electron pairs you got going on there, regardless if they're bonding or non-bonding. So once again, if we look at oxygen, which is 8, 1s2, 2s2, that's a lot of math there, 2p4, I think. There you go. So oxygen basically has our 2s that has a couple electrons, our 2p, which has 4 electrons, looking like this. So now as the hybridization process occurs here, this lower electron will now end up where? Gonna end up right there in the second spot, right? Because that's where it should now go. And when it does so, what will happen is we will end up with our 2s that has an electron, our 2p that has this, and this. Once again, the oxygen is going to hybridize as sp3, which means we're going to take all those guys there. And once again, we are taking 4 atomic orbitals, which then should give us 4 hybrid orbitals, which would be the sp3 hybrid orbitals. And once again, if we're kind of putting our electrons over, we got basically this happening. So if we look again, we can account for all the bonds and everything that's happening here. If we call this bond right here bond number 1, it could be from this guy in oxygen to a hydrogen 1s orbital, making bond number 1. Call this guy bond number 2. To be this guy going up again to a hydrogen 1s orbital, making bond number 2. And now we can see what is left is an unpaired electron, which would be represented by that. And one more unpaired electron, our lone pair there, which would account for that guy. So once again here, our hybridization accounts for both the non-bonding electrons that we see around the atom and also all the bonds that we see occur here. Any questions on that there? So we could also have hybridization. Yeah. It is for oxygen, yeah. So the hybridization here is happening with oxygen. Once again, hydrogen will not hybridize because it has basically just 1 electron. Everybody else could potentially go through hybridization. And potentially you could apply hybridization, although we do it a lot to the central atom, you could also apply it to outside atoms as well, but usually just not hydrogen. Other questions? So let's take a look at this guy here, which is C2H4. If we draw a little Lewis structure action here, something like this. All right, so we actually have 2 carbons here, right? We have 2 central atoms. We got carbon number 1 here. We got carbon number 2 here. Let us start with carbon number 1. What is the hybridization of carbon number 1? Sounded like a question, but you might be right. Let's see. So we got basically 1 electron pair, right? Just like we talked about geometry, we're basically just going to kind of put our hand on the right-hand side, Will. So we got 1 electron pair, 2 electron pairs, and once again, our double bond is going to count as only 1. So that basically is 3 electron pairs. And I believe you said it correctly, 1, 2, and 3 would give us a hybridization of an S. And I just marked off 2 p orbitals. So that is an sp2 orbital, our hybridization. The carbon on the right-hand side is frankly identical to it, so it will come out the same, but just to count it off here, that is 1 electron pair, 2 electron pairs, and once again, in the center would be 3 electron pairs, which would give you 1, 2, and 3 as well. So that would give you your sp2 hybridization here. So both of these carbons in this particular case is going to go through sp2 hybridization, and we could use hybridization to basically explain the bonds that we see here. So for example, we have a carbon that has 1s2, 2s2, and what do we have there? 6,2p2. So we got our 4 valence electrons for carbon. So carbon number 1 has our 2s electrons and our 2p electrons here and here. We're going to get the promotion that's going to come up to here. We're going to hybridize in this case sp2, which means we're just going to hybridize these guys here, right? So when we do that, we end up with 3 sp2 hybrid orbitals in carbon number 1 that each have an electron. And we actually have one unhybridized pz orbital that also has an electron, as it didn't go through hybridization, basically. Now, because the second carbon is pretty much identical to it, it will end up the same hybridization. So our second carbon over here will basically end up exactly the same. It will have its 3 sp2 hybrid orbitals, and also will have an unhybridized pz orbital. Any questions on that there? So now what we want to do is maybe account for all the bonds and everything that we see going on. So if we take our structure here, I'm going to redraw it over here. First off, the carbon number 1, which is on the left here, will make a sigma bond with a hydrogen. So we could take, say, one of these carbons here and make a bond with our hydrogen, 1s orbit. So that would account for, say, that bond right there. Also, we have the exact same bond, which is over here between the carbon number 1 and another hydrogen. So we'll take this one and I'll draw it down. So maybe it looks sort of like where it is there. We have the hydrogen 1s orbital bonding there. On carbon number 2, we have basically the same bond. So we have a bond between a carbon and a hydrogen. And we have one more bond between a carbon and a hydrogen. So that takes care of all those sort of bonds that are happening. So what is left that we haven't sort of accounted for in terms of bonds is the double bond between the two carbons, is basically what we got going on there. So when we look at the double bond between the two carbons, we also have a bond that's going to occur between the carbon and the carbon, and it's going to occur head on and make a sigma bond. So when we look at just the carbon-carbon double bond, I'll call this the first bond there. That is going to be a head-to-head sort of collision between these two guys. So these two guys here between the carbons will make sort of the first line of our double bond. Now, all these bonds that I just did and accounted for, these are all sigma bonds. So this would be a sigma bond. This would be a sigma bond. That would be a sigma bond. That would be a sigma bond. And the bond between there would be a sigma bond. Those are all sigma bonds. Those are all where the orbitals basically come right at each other and overlap, basically what is referred to as head-on overlap. And they just come straight at each other. I still have one more bond I need to account for, which is really the second line here, right, for our double bond. What is left to make that double bond line from? The only electron that's not accounted for in each of these carbons is the unhybridized p orbitals, yeah? So the pz orbital on the carbon on the left, the pz orbital on the carbon on the right that has an electron hanging out there, those are the only ones that are not accommodated yet in any type of bonding. And that is where our double bond comes from. It comes from the overlap of the unhybridized p orbital on this one carbon and the unhybridized p orbital on the other carbon. And it actually overlaps differently than a sigma bond. So a sigma bond, like I said, comes straight at each other and basically runs into each other. What happens with our p orbitals is it does what is referred to as sideways overlap. Above and below basically the plane of kind of the bond and where the atoms are, you get this kind of sideways overlap of those p orbitals. And this type of overlapping of unhybridized p orbitals are what we refer to as pi bonds. So these are pi bonds. So when unhybridized p orbitals overlap sideways, they create a pi bond. And that accounts for basically what happens here to make our second line, if you will, for a double bond is these two guys here will do that sideways overlap and create a pi bond and also the double bond. So as you can see here, our hybridization accounts for all the bonds that we have going on here, including the double bond. And as you can see, a double bond is really made up of two types of bonds. It's made up of a sigma bond and it's made up of a pi bond. So when you make a double bond, it's technically made up of those two types of bonds that are happening. Sigma bond, where we got guys coming at each other, and we have some unhybridized p orbitals just doing some sideways overlap above and below the plane of the molecule. And that's going to create basically the second bond, if you will, to create that double bond. Any questions on that there? So what happens when we get into, say, a triple bond situation? When we get into a triple bond situation, say like this guy here, and if we draw it, we got this thing going on. So we got carbon 1, we got carbon 2. Hybridization of carbon 1 is not everybody at once. Hybridization of carbon 1 is, what do you think? It is sp. It's got one electron pair here. And again, the triple bond, just like geometry, will count as only one. So basically it has two electron pairs, which means the hybridization of this guy is going to be sp hybridization. So this guy will hybridize as sp. Carbon 2 is identical. It has basically the same two electron pairs. So it will also hybridize as sp. Sp goes with what geometry there? Linear. Perhaps you built this one with a triple bond or something that triple bonded the other day. You should have saw the geometry straightened out basically as linear when you use the springs and kind of got them all in a triple bond or even a double bond. You might have saw it. So when we do this, we will look at our carbon. And once again, here our carbon has its 4 valence electrons. We're going to get our hybridization that's going to come up, and our carbon is going to end up hybridizing only the S and the P, so just one of those guys. The result of that is we're going to get 2 hybrid orbitals, which are sp. We hybridize an S and a P, so that's 2 atomic orbitals, gives us 2 hybrid orbitals, and this is carbon number 1. We will also then, in this case, have 2 unhybridized p orbitals, the px and the py and the pz orbital. Everybody here will have an electron, basically. The same thing is going to happen here with the second carbon because pretty much it's identical. So carbon number 2 will end up exactly the same way. Not always the case, but happens to be in this case here. Be sp. Also our pz, py, we'll go that way, and that. So once again here, we can basically account for everything that we see in terms of the bonds. We'll call this bond A here. So again, we would take an sp hybrid orbital and a hydrogen 1s orbital and make that bond. We got a similar bond on the other side. We'll call this one bond B. Going this way to a hydrogen that also is going to make that bond there. Those are both going to be sigma bonds, I guess. Basically, a single bond will be a sigma bond. So those are both sigma bonds in this case. Now what we have left is really the triple bond. So we already saw that in a double bond, it is made up of a sigma bond and a pi bond. So you can maybe imagine that a triple bond is made up of a sigma bond and actually 2 pi bonds is basically what will make up a triple bond. So the first sort of bond, if you will, for our line, our triple bond, we'll go with this one, is going to be the head-to-head overlap of those two electrons coming together to make really the first line in our triple bond. The second one will be now, the second and the third one are going to be a result of these unhybridized, very badly drawn. There you go, that's a little bit better. P orbitals here, and they're both going to basically make some pi bonds. So we will have a pi bond that will happen between these two guys here. Overdrew. Again. All right, so we'll have a pi bond between those two there. And we will also have a pi bond between these two here. And that's going to account for the second and the third line there in our triple bond. So what happens is, again, we get basically sideways overlap of the py atomic orbitals, making a second line, and then our second unhybridized p orbitals doing it as well. I'll draw it really crappily for you. I just give you that warning there here. So we got basically a set of p orbitals overlapping like this. We have another set, since they're on different orientations in three-dimensional space. And again, my really bad drawing, so I apologize in advance. We got these guys doing some other overlaps that are happening here. So both of them are basically overlapping sideways, creating basically the second and the third line, if you will, for our triple bond. Any questions on that? So in this case, we basically have 3 sigma bonds, this being a sigma bond, that being a sigma bond, and this being a sigma bond. And we have 2 pi bonds that are basically here as well. Any questions on any of that there? All right. Questions on hybridization? I think we got a couple more things to talk about here on that. Hang on. We also could hybridize, obviously, multiple bonds, which again are our pi bonds, as we were talking about. Again, a single bond, way to remember it's kind of quickly, single bond is a sigma bond. A double bond here is a sigma bond and a pi bond. And a triple bond is a sigma bond and 2 pi bonds basically that occur. We could also hybridize into our expanded octet, and that would get us into basically the Ds, right? And that's what happens in our expanded octet. We end up with 5 electron pairs or maybe 6 electron pairs that occur. So we can go through hybridization upwards of that as well through the basically trigonal bipyramidal and the octahedral geometries that we talked about as well. So for example, you could still do the very simple counting off method here. If I had a central atom that had something like this, this would have 1, 2, 3, 4, 5 electron pairs. 1, 2, 3, 4, 5. That's an S, that's 3 Ps, and that's 1 D. So the hybridization of this guy would be Sp3D. Same thing if you got to the octahedral. I'll just do them all as bonds. You have 6 electron pairs, which again would give you 1, 2, 3, 4, 5, and 6. So that's an S. That's 3 Ps. And 2 Ds. Yeah. So again, you could just simply count off hybridization. You will not be asked to draw any of the arrows and where they go or anything like that, but you do need to be able to identify the hybridization. And I think that is probably the easiest way to do it, is simply just count it off and stuff like that. Now, sometimes books will write it as like D, Sp3, put the D first. I don't know, it seems awkward to me. But sometimes you will see books write like the hybridization for these guys as like put the D first. I personally put the D last, but some books will kind of put the D first sometimes. Question on hybridization. So once again, like I said, you will not need to draw the arrows or anything like that. It's just supposed to hopefully help you understand where all the bonds and stuff come from. But you do need to be able to give the hybridization and sigma bonds and stuff like that. So with that being said, let me just draw a crazy molecule here for fun. All right, let's do this one. Let's do this one. So in each of these, tell me how many total sigma bonds are there and pi bonds. And also give the hybridization for each of the atoms that are highlighted here. So give the hybridization for this guy, that guy, that guy, that guy, that guy, this guy, and that guy. All right, take a minute, see what you come up with here. I'll do it as well since I just drew it. Take a look here. So once again, if I was going to do this, I would make my little sort of cheat sheet here, if you will. Again, just like on electron configuration. So we got our S, our P, and our D. So I'm gonna start with the hybridization. So I'll start, we'll start with this guy here, I think. Go with this guy. All right, so starting with this guy, I want to figure out electron pairs. You should have came up with 1, 2, 3, and 4 electron pairs, which means 1, 2, 3, and 4. So that should be Sp3 hybridization. Question on that one. Coming to the guy next to it, that would be 1 electron pair there, 2 electron pairs there. Double bond going to count as just 1 electron pair. So that would be 1, 2, and 3 electron pairs. So that's going to be Sp2 hybridization. Yeah. Coming to the next guy, we got 1 electron pair, 2 electron pairs, and again, double bond will only count as 1 electron pair. That's going to give us the exact same thing, 1, 2, and 3 electron pairs. That's going to be also Sp2 hybridization. Any questions so far? Coming to the next guy, we got 1 electron pair there for the double bond, 2 and 3. So once again, a nice little run here of Sp2, which would be 3 of them. And lastly here, we got 1, 2, 3, and 4 electron pairs. So that again would be 1, 2, 3, and 4. And that would give me Sp3 hybridization. Any questions on any of those there? Coming to the guy at the bottom there in the hybridization, nitrogen has how many electron pairs for this purpose? It has 2. 1 electron pair there. Triple bond counts as only 1. So that would be 1 and 2. So this is Sp hybridization. And so is its carbon friend on the other side. It has 1 and 2 electron pairs. So that is Sp hybridization. Any questions on how to identify hybridization? Yes. Keep it simple, just count, basically. Yes. Always start with S, work your way to P, then work your way to D. Yeah. Any questions on any of that? All right, sigma bonds here are basically all the single bonds we got going on there. So give it the old colors right here, not to erase the entire place here. Yeah, a little shot there, a little shot there, a little shot there. Perfect. All right, so basically for sigma bonds, it is easy way to think about it, really just like the single bonds, all the single bonds you got going on there. So on the top guy, that would be a sigma bond. 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 That would be, that would be, that would be, and that would be a sigma bond. Now, hiding in a double bond is also a sigma bond, right? Because the first line in a double bond would be a sigma bond. So that would be a sigma bond. And also over here would be a sigma bond as well. And that would give me, I'm not sure why I highlighted it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sigma bonds in this case. Yeah. Now, in terms of pi bonds, we have really just this one, right? So that one right there. And we would have one pi bond in this case. Any questions on that there? Now for the bottom one, sigma bonds, once again, would be our kind of single bonded. So that would be a sigma bond. And hidden in the triple bond would also be a sigma bond. So we got basically two. And the other two lines there in our double bond, triple bond is pi bonds. So those would be our pi bonds, which would be two as well. I think the only thing I missed was actually the hybridization of the oxygen up on top. Yeah. Yeah. There is. Thank you. I did miss that one right there. Thank you. There is. Thanks. That is the second one right there. It wasn't highlighted. Thank you. So it should be two. Thank you. Other questions on that? So in this case, I did miss also the hybridization of this oxygen, which we could apply hybridization to this guy. This would be 1 electron pair, 2 electron pairs, and our double bond here would count as just one more, which would be 3. So 1, 2, and 3. So that oxygen up there, if it hybridized, would be Sp2 as well. Any questions on how to assign hybridization, sigma bonds, pi bonds? They need to be able to obviously do that. You need to be able to draw the Lewis structure. You need to be able to draw the Lewis structure, give the electron pair geometry, give the molecular geometry, give the hybridization, all that fun stuff. Yes. Any questions on any of that? All right. Last thing we're talking about here, I think, is not that we just did. We're going to talk about molecular polarity here. So earlier we talked about, again, what's sometimes referred to as bond polarity. And a lot of times we do use bond polarity with the difference in electronegativity. So when we talk about bond polarity, that is usually when we use kind of our difference in electronegativity values. And as we talked about, I think in the previous chapter, bond polarity and molecular polarity are two different things in most cases. Bond polarity, using electronegativity values, for example, tells you simply between the bond between those two elements, are they going to be sharing them equally, the electrons, or unequally? We'll create a polar bond or non-polar bond between those two guys. When we talk about molecular polarity, we're taking into account everybody that's in the molecule, all the bonds that are present, the geometry that is present, and overall, does that molecule share the electrons as a whole equally or unequally? And if it does share unequally, it would be a polar molecule, and it would have what is referred to as a dipole moment. And a dipole moment is represented very much the same way that we represent bond polarity. It's basically an arrow that looks something like this, where this guy always points to the more negative side, either of the bond or the molecule. And the other side that makes like a plus points to the side that's more positive within the bond or the molecule as well. Now, again, polar molecules will have dipole moments. Non-polar molecules will not. And if it is a non-polar molecule overall, what that means is overall, the molecule itself is sharing all the electrons equally. So there is no side of that molecule that's more positive. There's no side that's more negative. It's kind of neutral if you want to think about it. There's really not charge sort of associated with a nonpolar molecule. As we might have talked about last time, really the easiest ones to determine whether or not the molecule is polar or nonpolar are diatomic molecules. And that is simply because in a diatomic molecule, you pretty much have one bond in the entire molecule, which means if that bond is a polar bond, then that molecule will be polar. And if that bond is a nonpolar bond, it will be a nonpolar molecule because the entire molecule is made up, frankly, of one bond only. So like when we have something like H2, clearly this is going to give us a 0 in electronegativity value when we subtract them. That would tell us that this is a nonpolar bond. But once again, because this is the only bond here in this particular molecule, it will tell us that this molecule is also a nonpolar molecule. Doesn't matter if it's single bonded, doesn't matter if it's double bonded in terms of polarity. Same thing here. These are both oxygen. The only bond that we have is this double bond between them. That is a nonpolar bond. And because that is, again, the only bond there, that would mean that this guy would be a nonpolar molecule. Each of those guys would not have a dipole moment. Basically, overall, because there's only that one bond, the electrons would be shared equally. There's no side that's more negative or more positive. Changes, obviously, when we get something like we also saw here earlier, HF. HF is a polar bond with fluorine being more electronegative, which if we wrote the bond dipole arrow, it would be heading towards the fluorine. And because this bond here is polar, and once again, just like above, it is the only bond there. That means that this would also be a polar molecule. And this would represent its dipole moment in this case. And what that means is, again, like we talked about, the fluorine side of this molecule would be more negative and the hydrogen side would be more positive, because ultimately the electrons are hanging out over there by the fluorine side, making it more partially negative, and the hydrogen side being more partially positive. So this is really the only place where bond polarity, where we use the difference in electronegativity values, and molecular polarity basically cross over. Now, if everything was this simple, that'd be great, but it is not. When you get things that are 3 or more atoms together, you basically have to look at a couple of things to decide whether or not it's going to be a polar molecule or a nonpolar molecule. So let's talk a little bit about what you need to look at. When you have 3 or more atoms, you need to look at, first off, are there polar bonds? So clearly, if there are no polar bonds, it's kind of hard to have an unequal sharing of electrons. So that would make it obviously nonpolar. The second thing that you need to look at is actually the molecular geometry. And that is the shape that we talked about there. So for example, if we look at our friend carbon dioxide here, look something like this. First off, is there a polar bond between carbon and oxygen? Is that bond polar or nonpolar? Like a 50-50 shot, yes. I look at the periodic table, which might be helpful. Carbon and oxygen are in the same row. And I have oxygen further to the right. So would that be a polar bond or a nonpolar bond? It should be polar, yeah. That would probably mean oxygen is more electronegative than carbon since they're sitting in the same row. You don't need the values to help you determine that. You just need like the periodic table. That means that this does have polar bonds and they would be heading towards the oxygen, which is more electronegative. So the first answer here is, yeah, we got some polar bonds. So you might be tending to think it has polar bonds, so it would make sense that this should be a polar molecule. But the second thing that we need to look at is actually the molecular geometry here. What is the molecular geometry of CO2? It is linear. The carbon has, basically, if we count up electron pairs, carbon has got 2 electron pairs, and it also has 2 bonds, and that is a molecular geometry of linear in this particular case. It's basically a straight line. I think you might have built it the other day. So what we have going on here is basically a geometry that's linear like my pen. We have oxygen pulling this way, but yet we have oxygen pulling the other way. I am actually pulling in opposite directions on my pen. My pen is going nowhere, yes? So even though it does have polar bonds in this particular case, because of the geometry here, they actually cancel each other out, and this would be a non-polar molecule. So this is a very good example that you can definitely have a molecule, you can definitely have a molecule that contains polar bonds, but because of the geometry will actually be non-polar. And that is because these bond dipoles here are vectors. Yeah. They have direction, they have magnitude, and then I fell asleep in physics. But I woke up afterwards just long enough to hear, in some cases, they add to each other, right? In other cases, they cancel each other out. Typically, they cancel each other out when they're headed in equal and opposite directions, or they're heading like right at each other in the same direction. So you can think about it, people think about it like pulling a rope in tug of war. You got somebody pulling opposite of each other, right? The little thing doesn't go anywhere. If you have like a door that swings and you have 2 people pushing on the door, right, equally, the door is not going to open one way or the other. So these guys can basically either sometimes cancel each other out, or they can actually add to each other. And because of the geometry in this case, they actually will cancel each other out. So whenever you get these guys kind of heading in equal and opposite directions, they will cancel. And when they do not, they will not cancel. So if we look at another example of our good friend water here, that's a bad drawing of water, but we'll work with it. So we have water, and the bond between hydrogen and oxygen, polar or non-polar? It is polar. Thank you. Gonna walk out in a second. All right. And this bond would also be polar, heading towards the oxygen, as oxygen is more electronegative. So here our water also has polar bonds. Now we want to think about the geometry here. Geometry of water is bent or V-shaped, right? It's got 4 electron pairs and 2 bonds. So that is our bent or V-shaped, you know, like a Bucko 4 or something like that. So what we have in this particular case is this kind of V-shaped geometry sort of drawn. So what we have in this case is kind of like this deal, and we got a polar bond coming this way, kind of meeting at the top, almost like if you had a string on top and you pulled, right? The whole thing would kind of move. And in this particular case, we get a net dipole moment heading in this direction towards the oxygen, where it will be more electronegative, or more negative towards the oxygen side, more positive. I woke up and it was something like you do this move, right? Then you connect them, kind of coming that way, right? So then I fell back asleep because it was a boring class. So we ended up with a case here where they do add to each other because of the geometry, and we will get a polar molecule in this case because of that. Now, frankly, who wants to draw vectors? Maybe you do, I don't know. But if you like vectors, draw them. I'm just kidding about it being boring. It's not. But there are certain geometries that are considered symmetrical geometries, and there's certain geometries that are considered unsymmetrical geometries. And the geometries we're talking about here are the molecular geometries. So if you have some symmetrical geometries, And in our case, you got some good lists here. I think you got a trigonal planar. You got a tetrahedral. And again, this is the molecular geometry. You got a trigonal bipyramidal. Got a little octahedral action. So what these guys all have in common, if you remember when you drew your Lewis structures, are when you draw your Lewis structures, there are no dots on the central atom. So if you draw one of these Lewis structures that have this molecular geometry and you got no dots on the central atom, and all the outside atoms are the same element, it will be a nonpolar molecule in most cases. So for example, if you had this deal here, I won't finish all my dots, but we'll just draw this. Between carbon and fluorine, right? There is definitely polar bonds, right? Fluorine being more electronegative. So if we look at this here, this is a central atom where I don't see dots. Everybody on the outside is the same. This is going to be non-polar. They will be tetrahedral from each other. They will basically cancel each other out. Now, what would happen though if I took one of those fluorines off and replace it with our friend hydrogen? Again, in this case, we have the polar bonds kind of heading in this direction, not drawn three-dimensional. We would have polar bonds going this way, right? What about hydrogen? Carbon hydrogen, is it polar or non-polar? It is non-polar. It's the difference of 0.4, so it's considered non-polar. Even though it's not perfectly zero, it actually is kind of heading a little bit towards carbon, but it's still considered non-polar. So for all intents and purposes, we got these three guys kind of pulling, and this guy really not pulling the opposite direction. He's just going to actually go with them a little bit. And you could kind of envision it moving, if you will. So it would go from a non-polar molecule to, in this case, a polar molecule. So if you got any of these symmetrical geometries and everything on the outside is the exact same element, it's a safe bet to write non-polar. If you have no dots on your central atom in one of these geometries, but they're not all the same element on the outside, it's probably a safe bet to write polar in most cases. Any questions on that there? Yeah. Something like carbonate, right? It's got the double bonded. Yeah. So again, something like carbonate, for example, would be non-polar based on geometry here because it has basically the 3 electron pairs and 3 bonds. Yeah. Other questions? So that leaves us some unsymmetrical geometries, which I will do here, I think. Get rid of this. So some unsymmetrical geometries you got going on here. You got a good list. You got angular. We got our trigonal pyramid. We got our bent, our V-shaped. We got our seesaw. We got our T-shape. We got our square pyramid. What all these guys have in common is when you draw the Lewis structures, we have dots on the central atom. And if you draw Lewis structures, you end up with one of these geometry with dots, and all the elements are the same on the outside. It will most likely be polar molecule. So that's, for example, if we just looked at our water without doing any vectors, I see dots, I see everybody the same on the outside, I see polar. Yes. I see something like this. This guy would be polar or non-polar. This would be polar. Yes, I got dots on the central atom. I got everybody on the outside the same. That's going to be a polar molecule as well. So this guy here, polar or non-polar. It is going to be polar. We got dots. We got everybody same on the outside, going to be polar. So you know how quickly you can kind of do a lot of these guys. just by looking at it. We have this guy here, polar or non-polar. I want all the dots on the outside. Yeah, it would be non-polar, kind of like CO carbonate there. We have basically no dots. Everybody on the outside is the same. So this would be non-polar as well. Now, there is a couple of exceptions where you can have dots on the central atom, but the polarity will be non-polar in most cases. And those couple of exceptions are going to be linear, and it is linear with 5 electron pairs and 2 bonds. They are expanded octet linear, and also our square planar, which is also 6 electron pairs and like 4 bonds. These two guys, when you draw them, will have dots on the central atom, but because of their geometry, they will still end up being nonpolar. So for example, our linear guy, right, looks something like this. So even though it's got the non-bonding electrons to make a triangle, but we basically have our linear guys opposites of each other. So this guy would be nonpolar, even though it's got dots. And our square planar, which would look something like this. You got some dots coming out this way. But basically, because these guys make a square, they're pretty much equal and opposite of each other. So they will cancel each other out. And our non-bonding electrons will also cancel each other out. So those are 2 exceptions to the quick rule of if you do have dots and you have either of those 2 geometries, it will most likely be nonpolar if everything on the outside is still the same element, because again, they will cancel out. So those are the only 2, and these are the expanded octet guys that will be the exceptions. Question on molecular polarity, yes. Yeah, so it'd be kind of like this other symmetrical. So it would most probably in a case change then to being polar in that case. But if everybody's definitely the same on the outside, because they're kind of symmetrical, makes a square basically, they'll cancel out of each other. Yeah. Other questions? All right, that's fun stuff. Yes.